Hi Satvik, I guess we'll get started in 5 to 10 minutes. I'm just waiting for a few more people to join the session in person. So I guess we'll get started in uh, 5 10 minutes. Well, like if no one else joins, I'll just I'll just start addressing you on YouTube audience. Okay. So I guess no one else is joining the session in person. So I think we can just get started. So just to reintroduce myself, so hello everyone. I'm Lakshya Saggi, the problem solving TA for the NPTEL Games and Information course. And this will be, I believe, our 10th session. And in this session, we'll be discussing problems related to Bayesian Equilibrium, basically that and like Stackelberg games, the topics which were covered in this week's lectures. So without further ado, I guess I'll just get started with discussing the problem statements for today. Let me just share my screen here. Okay, okay, so I hope my screen is visible to everyone. If it is not, please let me know via chat because I'm like I'm not on my laptop but on a different laptop today, so like, there might be some technical issues. Just let me know, guys, if you can see the screen. Okay, it's visible. That's nice. Okay, then. So I guess we can get started. So. Yeah, till previous weeks, I think a lot of the concepts which were covered were more theoretical, and so what we were doing was for 1 or 2 weeks we were discussing a bit of theory first, and then coming to the questions. But I think in this week in Bayesian equilibrium, I think a lot of things were, a lot of topics were indeed like uh, less theoretical, less about proving stuff and more about practical things like finding out the Nash equilibria and everything. So I think. Uh, we'll just get started with the questions straight away. So maybe just have some warm-up questions based on the theory first, and then we can have some. Yeah, we can have a few questions based on Nash equilibrium. So the first question just states that in a finite game with two players, there always exists more than one Stackelberg equilibrium pure strategy. True or false? So I'll be assuming that everyone has I'll be assuming that everyone has gone through the lecture videos for this week, and after so we'll be focusing more on these problem statements only. So the first question is this, guys. Based on theory only. Like in a finite game with two players, there always exists more than one Stackelberg equilibrium and pure strategies. So is this statement true or false? So I hope everyone remembers what's Stackelberg equilibria. So Stackelberg equilibria is in the games where there's some notion of a leader and then there's a follower, and then leader has a strategy which he publicly makes known to like the followers, and then since the followers already know the leader's strategy, they have to make the strategy accordingly. And now what the leader actually wants to do is so the leader knows that the follower will be maximizing his payoff given any strategy. So now leader has to choose one strategy so that uh, in accordance with the follower response, the leader's uh, payoff is maximized. So that kind of a thing. So would anyone like to answer this question in chat? Uh, Manas or Satwik? What do you guys think? So do you think that there will always exist more than one? So there will exist more than one Stackelberg equilibrium pure strategies. First of all, I think the notion of Stackelberg equilibrium is clear, and like what are pure strategies? So pure strategies are where players are playing only uh, like deterministic strategies. They are not using randomization. So actually, yeah, actually this thing would be false. It's not true, huh? Okay, so Manas is saying true. So Manas is saying in the chat that for a particular leader, there will be one action that will do the job. So yeah, Manas. Uh, so Manas is like, so Manas is claiming that for a particular leader, there will be one action that will do the job. So that's correct, Manas. So like you can say that for every pure strategy of the leader there will be like some payoff associated to that strategy. And how will the leader obtain that payoff associated to the strategy? It will be the payoff corresponding to that strategy comma uh, the follower's best response to the strategy. So the payoff associated with the leader's own strategy and the follower's best response to the strategy. And with this pair will constitute the leader's payoff. So they will always, and then you have to like kind of maximize your payoff over all the strategies. So so there will always exist at least one maxima. So you can say that there will always exist at least one Stackelberg equilibrium in pure strategies. That you can always claim because of this argument, because there will always exist a maximum. So there will always exist at least one Stackelberg equilibrium. But I think the question here was like designing that. So your reasoning is correct, Manas, but the question asks that not just one, it says that there will always exist more than one. Like I'm not asking for greater than equal to one, I'm strictly asking for more than one. So this is like trivially incorrect. Like it there can be possible cases, right, where there is exactly one maximum. There is not more than one maximum. So does this make sense? Like just think of it as like suppose the leader only has one strategy, then that strategy will be the Stackelberg equilibrium itself. But we are asking, does there exist more than one Stackelberg equilibrium pure strategy? So if there is only one pure strategy, how can there exist more than one uh, Stackelberg equilibrium pure strategies? So does this make sense, Manas? Like your argument is definitely correct that there will be at least one action that will always do the job. But I'm not asking for at least one. I'm asking for great more than one. So yeah, this question is like not very interesting, but I just wanted to highlight that yeah, like we always talk about like there will be at least one Stackelberg equilibrium pure strategies, but it need not mean that there will always be more than one. There can be cases where there will be a unique Stackelberg equilibrium pure strategies. So in that case, yeah, maybe we'll get to that later, but yeah. So I'll just say that the answer is false. Uh, as there can be uh, games where the leader has exactly one strategy which maximizes the other payoff. Like I don't think we even need to give an example for this. Like you can just think that just think of a game which has exactly one strategy for the leader, and in that case, it will be triple good. The main notion why I wanted to give this question was not because like okay you might think that this question is trivial, but what I wanted to say with this was since there can be cases where there is exactly one equilibrium pure strategies, then in that case there like if exactly one equilibrium exists in pure strategy, then it might be the case that like there may not exist any other equilibria even in mixed strategies. So it might be the case that there is exactly one Stackelberg equilibrium and it is in pure strategies, and no mixed strategy equilibrium exists other than this pure strategy equilibrium. That's the main idea why I wanted to give this question. That it might be that mixed equilibria may not exist except for a pure strategy equilibria in a Stackelberg game. Okay. Then again, I think So the second question is also just a theory-based question, like to pick the correct option. So there are just two options. The optimistic and pessimistic formulation of the Stackelberg game differs in the objective of the follower in both settings, and the B option says of optimistic and pessimistic formulation differs in objective of the leader in both the settings. So I hope everyone knows what this optimistic and pessimistic formulation of the Stackelberg game means. So as we discussed in the previous question, also like there may exist more than so there can be cases where there can exist more than one equilibrium and pure strategy, right? Then how do you determine which equilibria do you want to choose? So in that case, like it's up to the follower to choose like which equilibria the follower, the leader basically. It's up to the leader which equilibria the leader wants to have. So optimistic formulation is a formulation where the leader believes that the follower will do like what's best for the leader, and pessimistic formulation is an assumption where the follower will do worse for the leader. So these optimistic and pessimistic formulations are basically the assumptions for the leader. So these are in the objectives of the leader, not the follower. Like leader has to choose which equilibrium he wants to achieve. So like yeah, so Stackelberg game does not differ in the objective of the follower, but rather it differs in the leader, I think. So this is option B, and I would say this is like something which was already discussed in the lectures. So yeah, maybe I should have these as discussed in the lectures. I hope this is clear. I'll just underline this. And then maybe we can move on to the third question. So Satvik and Manus already wrote like option B is the correct here. So good job, guys. Just I wanted to make this notion clear that optimistic and pessimistic formulation, you know that they're different objective of the leader, but they don't have any relation to objective of the follower in any case. Okay. You can define maybe some other games where like I don't know, like they are not called this optimistic and pessimistic formulation, but you can define some games, right? Where you think that the follower will also have some kind of a favored best response. But yeah, let's not get into that. Uh, let's just stick to what we know and what we want to know. Okay, then maybe we can move on to the third question. Third question is that consider the following game with incomplete information. So this is a bit more interesting question, I would say. Yeah. So, so there are two players, both of whom want to maximize their payoffs. The player one only has one type, and player two has two types. And like basically, the probability that both the players have their first type is equal to the probability that both the players have the second type, and the probability is actually equal to the half. So basically, both the types occur with probability half for player two, you can assume. So every player has two possible actions, and state games are given by the following matrices. So this is the state game if so left part is the state game if uh, the type if the second player achieves type 1, and this is the game if the second player achieves type 2. So these are the payoff matrices for the two games. And now we have the and now we want to find out just like the question just asks us to find out the Bayesian Nash equilibria for this game. So in this game essentially like there are two types for player two, so you can actually think of this as a three-player game, like this was discussed in the lectures, right? That different kinds of if there are more than one type, then every player per its type can be thought of as a new player. So this instead of thinking of this as a two-player game, you can think of this as a three-player game also. But yeah, let's not get into that and maybe just stick to the question. So the question answer, like which of the following options will be a Bayesian equilibrium of the game? Okay. So maybe we'll have to just try it out option by option. Let's just do this option by option. So option A is something like this. Should I zoom out a bit? Okay. So The option A essentially says that the mixed strategy for player one will be uh, to play like two with 2/3 probability, basically top, and like yeah. So essentially like so this is the so this is the sigma two of player two will be like if player two has like a type two, then what this is the strategy play. I hope you get the notation that this is the probability distribution of the strategies for player 2 if it achieves type 2. Like this is the probability distribution for player 1 if player 2 achieves type 1, and this is like the probability distribution for player 1 if it like if it achieves type 1. Okay, I think there is a bit of a notational issue here. uh, yeah, I think yeah, I think this should be sigma 2. Yeah, we are talking about like strategies for there will be like two kinds of strategies for player two for different games, but player one only has one type, so he'll have only one type of strategy. So yeah. Okay, so maybe let's start with option A. So what do you guys think? Will this be a Bayesian Nash equilibrium? What do we want to see for identifying whether something is a Bayesian Nash equilibrium or not? So maybe let's just see first the player who has only one type. So let's just see the strategy for the player one. So player one plays like T with probability 2/3 and B with probability 1/3. And then what we essentially want to ask is like what will be the expected payoffs in this strategy? Like if player one plays like this with probability 2/3 and this with probability 1/3, then what you essentially want to check is he does not deviate from any of this. If the other player has some kind of best responses in these kinds of games. So should I do it, or would you guys like to answer this? Uh, would you guys like to try this option first by yourself? So maybe like for this option, like for option A, just try and like I'll give you like 3-4 minutes and just try it out whether this will be a Bayesian equilibrium or not. After that, we'll also discuss this. So I'll be muting myself, I guess, for 5 minutes, and you guys can think about this. Will this be a Bayesian equilibrium or not? So if you guys kind of want a hint to try it out, so we know that player one only has one kind of type. So player one can only play like player two can have like a different probabilities for these two games, but player one will always play like like uh, T with some probability and B with some probability, and it will remain the same for like both the pair of matrices. And the value given to us here is like 2 by 3 comma 1 by 3. So essentially what you need to check is like if player 1 plays this with probability like with T with probability 2 by 3 and B with probability 1 by 3, then like since this is a mixed strategy, what you would want is the expected payoffs like it should be indifferent between like T and B. It should not have something like different strategies. And also like since this is also playing like a mixed strategy, then you also want at this like if player one plays 2 by 3 comma 1 by 3, then the player 2 should also be like uh, should not distinguish between payoffs of L and R given player 1 plays 2 by 3 comma 1 by 3. If these kinds of conditions hold, then maybe you can say that it's a Bayesian equilibrium, otherwise you can't say. Okay, maybe since no one is answering in the chat, uh, we can just get started with the discussion. So, should we solve? Let me just think. Should we solve this problem in general or just for this? Maybe we should just solve for this specific case. Mm, okay, maybe we should solve the problem in general. Okay, so yeah. So let's just assume that player one plays like with probability p the row t and with probability b with probability 1 minus p the row b. So since p1 has only one type, plays p with probability p and okay, small p and b with probability 1 minus p. Okay, and note that we are just talking about mixed strategies here. We are not talking about any pure strategies. So yeah, we'll just get to that later. Uh, but p2 plays. Maybe I should just also p2 plays. Mm, if p2 is of type 2 1, then he plays uh, L with probability q1 and okay, and R with probability 1 minus q1. Similarly, so we are just defining the variables for now. I'm just trying to solve this problem. So if p2 is of type 2, then he plays L with group. So essentially, like we are just defining the problem statement for now. So the problem statement can be formulated numerically as follows: that P only has one, P1 only has one kind of type, so he can only like have one set of strategy like playing T with probability small p and like B with probability 1 minus p. But if P2 like, but P2 has like two different types, so you can have different strategies for these two different types. So if he's of type 1, then his strategy might be to play q1 and 1 minus q1. If he is of type 2, then his strategy might be to play q2 and 1 minus q2. Okay. And now what we want to find out is what happens at Nash equilibrium, right? Uh, since like okay, like maybe we can do a shortcut for this question that we know that player one is always playing a mixed strategy, or maybe like hmm, should we do this? Okay, let's just see what happens. Okay. So suppose like so let's for now let's just assume that like maybe we are checking for option this. So let's just assume that P2 is playing some kind of a pure strategy. So this can be one of the possible Nash equilibria, that if P2 is of type 2, then he plays a pure strategy of 0 comma 1. So now like we'll try out option A. So since uh, if P2 when of type 2 plays the pure strategy 0 comma 1. So what this means is that in this payoff matrix P2, the column player, is playing the strategy 0 comma 1. So essentially he's saying that the L is played with probability 0, whereas R is played with probability 1. So if R is played with probability 1 and L is played with probability 0, in that case what will be the best response, like if this kind of a thing happens? Or maybe we should not okay guys, sorry for the confusion. I'm just thinking of what's the best way to move about in this question. Okay, so this is 2 by 3 comma 1 by 3. Give me 1 minute guys. So this is 2 by 3 comma 1 by 3. Okay, maybe we can say that these are mixed strategies, so their payoffs will be kind of equal. So yeah, maybe let's just do it like this, right? So we know that okay, sorry for this. So we know that sigma 1 of L1, so this is like player 1 strategy. So we know that player 1 is playing kind of a mixed strategy here, right? So player 1 is playing T with some probability and he's playing B with some probability. So maybe this is the best way to solve the problem. Like this will get us to the solution faster, right? So since P1 plays a mixed strategy, like P1 is playing the strategy of 1 by 2 by 3 comma 1 by 3, so he's giving weightage to like both T and B. So this means that the expected payoff on playing T or B should actually be equal. Otherwise the player one would have strictly preferred one over the other. Since P1 plays a mixed strategy, uh, this means that the expected payoff on playing T, okay, should I put the question on the next page? The expected payoff on playing T is equal to expected payoff playing B. So expected payoff for P1 on playing P is equal to expected payoff for P1 on playing P. So what this means is that you can form an equation for the expected payoff. So uh, if P1 is playing this with probability P and this with probability 1 minus P, what this means is that the expected payoff for P1 will be, so with half probability we are in this game, with half probability we are in this game. So let's just look at like a payoff on playing T. So payoff on playing T will be, with half probability we will be in the first game, and in the first game, if the player is playing T, uh, so if the player is playing T, then the payoff will be essentially like this. L is played with probability Q1. So player 1's payoff will be 10 times Q1. 10 times Q1 plus this will be just 0. So 0 times 1 minus Q2. 1 minus Q. 1 minus Q. Okay. And similarly, if you are in the other half, like with half probability, suppose this realization is this, the game's realization is this. In this case, again on playing T, T, the payoff for player 1 is like 10 times Q1 plus 0 times. Okay, 10 times Q2. 10 times Q2 plus 0 times. I'm struggling a bit on this. And now what should this be equal to? So this is the expected payoff we get on if the player 1 is playing like T. Like if the player 1 plays T, then the expected payoff will be like with half probability you are in this state game, because like both the games occur with half probabilities, it's given to us. And if you are in this game, then like column player is playing Q1 with the column player is playing L with probability Q1, and this with probability 1 minus Q1. So payoff on playing T will be this, and similarly in the other setting it will be something like this. And what should this be equal to? This should be equal to the payoff on playing like on playing capital B. One second, guys. Yeah. And now what we have here is so on playing B, what's the payoff for like player 1? So it's like uh, 0 times Q1 if the column player is playing, and like this R gets realized with probability 1 minus Q1, and the payoff here is 5. So it's like 5 times 1 minus Q1. Right? And then there will be another half because of the other game, and in this other game again the same kind of expression goes through. It's something like 0 times Q2 and 5 times 1 minus Q2. 5 times 1 minus Q2. Okay, so this is the first condition which Q1 and Q2 will have to satisfy, and maybe what we get from here is, maybe let's just simplify the equation. So it's something like so this will become 5 times Q1. So this will become 5 times Q1 plus 5 times Q2 should be equal to, this will be equal to 5 by 2 plus 5 by 2, which will be 5. So 5 minus 5 by 2 times, it easily simplifies Q1 plus Q2. Like I just did like this side will be 5 Q1, this term will be 5 Q1, this term will be 5 Q2, so that's 5 times Q1 plus 5 times Q2, and this term will be like 5 by 2 minus 5 by 2 times Q1, and this term will also be 5 by 2 minus 5 by 2 times Q2. So this will 5 by 2 and 5 by 2 give a 5, and then this will be 5 by 2 times Q1 plus Q2. And what this gives us is something like so like you can just cancel 5 from everywhere, and you will get something like 3 by 2 times Q1 plus Q2 will be equal to 3 by 2 times q1 plus q2 will be equal to 1, and this implies q1 plus q2 should actually be equal to 2 by 3. So this has what has been written by Manas in the chat also. So good job, Manas. So this is one condition which needs to be satisfied. Right. So now we come to know that q1 plus q2 should actually be absolutely be equal to 2 by 3 for so this should be true if like the player one is playing a mixed strategy. This has to be absolutely true. So and like so let's just check in this option whether this condition is going to hold. So q1 here is 2 by 3 and q2 here is 0. So at least this property is holding, that q1 plus q2 is actually coming out to be equal to 2 by 3. So at least we know that this kind of a property holds in this, but note that this is like just upholding of this property is not enough. Like in a Bayesian equilibrium, like in an equilibrium, what we want is no one should deviate from their like commitments, like or their strategies. So right now we have just said that the payoff for like T and B will be equal for player one. So player one kind of right now has no use of deviating from any strategy, right? So suppose like, but we need to also see if yeah, if player two kind of any has if player two has a use of like kind of deviating from any strategy or not. Okay, so like at least we know that the payoffs are equal, so at least this condition is satisfied. But now we need to also like ensure that uh, other players are also like kind of not deviating from their strategies. So let's just see if the player q2 has like if the player 2 has any like incentive to deviate from his or her strategy. So let's just see like will player q2 like deviate from this strategy of playing like 0 comma 1. So let's just see here. So in this strategy, like we know that right now player one is playing t with probability 2 by 3 and this with probability 1 by 3. This has 2 by 3 probability, this has 1 by 3 probability of playing. And now we need to check the payoffs if the player 2 is playing L and if the player 2 is playing R here. Why is that the case? Because like if something is strictly better than the other, then player 2 will have an incentive to switch to that strategy like out of L and R. So maybe I'll just mention this. So condition 1. Okay. So now maybe I'll just mention that. Note that condition 1, just checking, condition 1 is not sufficient as we also need to ensure that player 2 does not deviate from his strategy. Like, we know that player 1 won't be deviating from his strategy, and why is this the case? Because given any strategy in which q1 plus q2 is equal to 2 by 3, player 1 can always player 1 always is ensured that in playing t or b, like his payoff will be the same. And like you can check that like yeah, so the player 1's payoff will always be the same if q1 plus q2 equal to 2 by 3. So player 1 has no incentive to switch, but player 2 might have an incentive to switch. So we need to check if player 2 is switching or he's not switching. Okay. As it just ensures that p1 will not deviate. But you also need to ensure that p2 does not deviate from his strategy. So like let's just check for P2. Checking with P2 deviates. So maybe I'll just we'll just try to do this a bit orally at first. So let's just see. So this strategy T is being played with probability 2 by 3. This B is being played with probability 1 by 3. Right, in this kind of a game, like we know that, like I'm just now checking for option A right now. So in option A, I know that T is being played with probability 2 by 3 and B is being played with probability 1 by 3. So what's the expected payoff if the player 2 plays the strategy L? So suppose in this game, if the state realization is of this payoff matrix, then if the strategy, if the pure strategy is just to play L by the player 2, then his payoff will be something like 2 by 3 times 0, because this is played with 2 by 3. So 2 by 3 times 0 plus 1 by 3 times 5. So his payoff will be 5 by 3 on playing L. But on playing R, uh, his payoff will be like 2 by 3 times 10 plus 1 by 3 times 0. So this will be something like a 20 by 3. So note that playing R is strictly better in this case for player 2. And that's why he'll play the pure strategy of R. So at least we know that this part is correct, that if player 1 is playing with probabilities 2 by 3 comma 1 by 3, then player 2 will like stick to this 0 comma 1 strategy in this game, in this realization of the game. But suppose the game is realized in this manner, then also we need to check if player 2 has any incentive to play one strategy or the other. So here we know that like this is being played with 2 by 3 and this is being played with 1 by 3. So what's the player 2's payoff on playing L? It's something like 5 times 2 by 3, which is 10 by 3 plus 0. So on playing L, player 2's payoff is 10 by 3. And here also you can see that it's like 2 by 3 times 0 plus 10 times 1 by 3, which is again 10 by 3. So player 2's payoff is equal on playing L and R here. So actually player 2 can play any mixed strategy, because payoffs on playing L and R is the same. And that's why this, like player 2 won't be deviating in this type of in this realization of the game either, because L and R are equal, so player 2 can play any mixed strategy. So maybe I'll just mention in the first realization of the game, which is like, okay, how is this written? In the game, payoff for P2 if P1 plays 2 by 3 comma 1 by 3, then the payoff for P2 on play L is payoff for P2 on playing R, which is equal to 10 by 3. Hence P2 does not deviate from this current strategy in this realization. So we have just checked for like this game. So I've just been for this game, and now similar argument will need to say for this game. Maybe I'll put this in some kind of related format. That it show readable or something. Just checking here in the 1 comma second realization of the game. if P1 plays like again P1 is playing like 2 by 3, 1 by 3, payoff for P2 on playing L is actually something like here payoff for P2 on playing L was something like it was like something like 5 by 3, whereas it was 20 by 3 here. So here it was 5 by 3, whereas payoff for P2 on playing R is 20 by 3. Hence P2 strictly prefers R, and hence uh, is the strategy 0, realization, right? So so P2 does not deviate here, P2 does not deviate here also, and we know that for P1 the payoffs were like, for ensuring that payoffs for playing T and B were equal, we just need this property that Q1 plus Q2 should be equal to 2 by 3. If this is true, then we know that P1 does not deviate, and yeah, and I want P to deviate because yeah, P2 has this kind of value. So because of this, uh, so option A is a valid Bayesian. So it might be a bit confusing and it might be a bit involved, but that's precisely why I wanted to discuss this question, guys. Like I was a bit confused at first also how to like explain this, but yeah. But I think the correct way to explain this is looking at first the player with only one type and just saying that okay, like player one is playing like a mixed strategy here. So why is he playing a mixed strategy? Then it means that his payouts must be equal on both the strategies. And what's the condition on like and then we just applied the condition of payouts being equal. This ensures that player one will not deviate. But what stops player two from deviating? So we need again to check like in any realization of one player one's one strategy, we need to check if the other player is deviating, and player the other like, and we just check the conditions for deviation. Similarly, we can try for option B also. So maybe we should do option B also. Just okay, maybe. So this is a universal condition. So we know that like P1 is playing a mixed strategy in both of these options, right? Okay. So Manas has already done the calculations for option B, and he's saying that option B is also seems okay because payoff of player two is coming the same, and so mixed strategy is valid. And for type one, payoff is more in our case, hence 0, 1 is valid. Okay, so Manas is claiming that it is valid. So yeah, I think the correct answer is it is indeed valid. So good job, Manas. But maybe I'll just discuss this also, just so that like people can get a bit more practice and like get a better idea of what's going on here. So, so first of all, we know that P1 was playing a mixed strategy in both the options. It means like the first condition which we need to ensure is this condition. So this ensures that P1 will not deviate. So at least we know that P1 is not deviating. And in this option also, we know that Q1 plus Q2 is 2 by 3. So this is ensured that player 1 is not deviating. Now we have to check whether P2, the player 2 is deviating or not. So we check this in option A, and now we'll be checking this in option B also. So maybe I'll just discuss option B for earlier because, and we'll just have some same kind of arguments here also. So in option B, if we want to check if P2 deviates, what we need to check is, so in this kind of a game, in let's say in this game, what's going to happen? So now the probability for player one, probabilities for player one are 1 by 3, 2 by 3. So T gets played with probability 1 by 3, B gets played with probability 2 by 3. So what are the payoffs for player 2 on playing L and playing R? Let's see. So on playing L, the payoff for player 2 is something like this is played with 1 by 3. So 5 by 3 plus 0 times 2 by 3. So on playing L, the payoff is 5 by 3. Whereas on playing R, the payoff you can see is 20 by 3. So yeah. So here actually the arguments will get actually reversed. So if player 1 is playing something like 1 by 3, 2 by 3, then the payoff for P2 on playing L will actually be so actually like these options will get reversed. Okay, just I'm just copying the text, like don't mind guys, but yeah. So what we are saying is in the first realization of the game, payoff for P2 on playing L is something like a 5 by 3, and whereas on playing R it is actually equal to something like a 20 by 3. So P2 strictly prefers R and hence plays the strategy in this realization, and we know that player 2 is indeed playing this strategy in this realization. So this is correct, and now we need to check in the second realization of the game uh, if P2 is deviating or is not deviating. So we need to check in this realization the payoffs on playing L and the payoff on playing R, where when like T is played with probability 1 by 3 and B is played with probability 2 by 3. So here the payoff on playing L will be something like 0 times 1 by 3 plus 5 times 2 by 3, which will be equal to 10 by 3. And on playing R also you can see it will be 10 times 1 by 3 plus 0 times 2 by 3, which will be again 10 by 3. So like if P1 is playing something like 1 by 3, 2 by 3, then payoff on P2 on playing L is equal to payoff on playing R, which is equal to 10 by 3. So again, P2 does not deviate here also. So option B is also valid, Bayesian equilibrium. So we have checked that P2 is not deviating in both the realizations of the game, and we already know that P1 won't deviate because his payoff is the same. And so, yeah, we have that uh, both of these are not deviating. So the answer is actually both. So yeah, both the options are valid Bayesian. Yeah, it might like the underlying concept is quite simple. We just need to check deviations and all, but like sometimes the calculations and just getting the whole picture of the situation might get a bit tricky. So I think it's important to discuss these kinds of questions. So now let's move on to the fourth question then. So fourth question says that consider the following game with complete information. So there are again two players, and there is a k which either takes the value 0 or it takes the value 3. And like it takes the value 0 with probability 1 by 4 and 3 with probability 3 by 4. And now both the players are maximizing utilities. Every player has two possible actions. Player 1 is row player, player 2 is column player. So this is the payoff matrix for the row as well as column players. Yeah, so Manas is saying that somebody has to come up with a systematic way to do this. Otherwise, for more number of types, this seems very tedious. So yeah, exactly, Manas. So like there is indeed a very systematic way to all of this. So the systematic way is actually like okay, like first of all, maybe like how would you approach the systematic way? You just check first of all for like all the corner points, like in terms of pure strategies, like assigning zero ones to everything and just checking whether any equilibriums exist in like 0 1 formats or not, right? So you can assign like 0 comma ones to all of these strategies and find out if the Nash equilibrium. So like checking if like given any strategy, like given any realization of the strategy, then it's quite easy for one to verify if that strategy is indeed a Nash equilibrium or not. Like suppose I just gave you this kind of a thing, like whether this is a Nash equilibrium or not. then the only thing which you had to check was for all the mixed strategies, you just had to check whether the expected payoffs are equal in both the strategies. So that's just a straight up application of the payoff matrices and the formulas. Like if you are given one mixed strategy, then you just have to check whether uh, on each of these strategies, like whether this kind of a thing is fixed, whether like payoffs are equal or not. Similarly, if this is a mixed strategy, then you have to check like if you keep every other thing as same, are the payoffs on playing this strategy or this strategy actually equal? And similarly, when you look at this specific strategy, then also you have to check if this thing and this thing, like under these assumptions, like so for any one condition, you need to what you need to do is like so if you need to check whether a player deviates from this kind of a thing, you need to check if like keeping every other thing same, what's the payoff on playing first strategy and what's the payoff on playing second strategy. So you just need to calculate like what's the payoff on playing this strategy and payoff on playing this strategy when every other probabilities are the same. And you need to do this for all of these three distributions. Like so you first fix this, like you first fix these two and check if on playing this or this whether the things are equal. Similarly, then you fix these two and check on playing this or this whether the things are equal. Similarly, on playing like similarly, then you can fix these two and like check whether this is equal to this, or like if one is strictly better than the other. So like given a set of probabilities, like there is a very systematic way, like given one set, there is a very systematic way to find out if it is indeed a so given any point, you can easily find out if it is indeed a equilibrium point or it is not. The tricky part comes in like going through all of these points. Like given any point, you can find out like given any set of strategies, it is easy to check whether one is deviating or one is not deviating. But the systematic way, like as you can see, like it can be exponential in size. Like you first have to fix two conditions and then check the payoffs, then fix these two conditions and then check the payoffs, then fix these two conditions and then check the payoffs. So it might be a bit tedious and everything. And that's why like we kind of try to look at it in a more general sense, like what is actually happening, like what are the equations and what's actually happening. But all of this can be automated with ease. Like if suppose I tell you that I have a computer with infinite computation power, I don't care about the time it takes, then this can easily be automated, like this procedure. So do you get what I'm trying to say, Manas? Why can this be automated? Like just checking if one point is a equilibrium or not. Does it make sense? Yes, exactly. Yeah, this is like exactly like finding out a Nash equilibrium is NP hard. So yeah, you have got the correct intuition of the NP hardness. So indeed, like this is a very common, like computing a Nash equilibrium is an NP hard problem in general games. Like if the game has some specific structure, like we had dynamic games in feedback form or everything, then uh, you can have. But in general setting, like if you are given like arbitrary payoff matrices and types, then actually the problem of finding even one Nash equilibria is NP hard. So yeah. So now maybe we can move on to the fourth question. So fourth question is again again a question which might seem a bit tedious. So again we have a payoff matrix and like note that the payoffs are dependent on k and k takes the value 0 and 3 with probabilities 1 by 4 and 3 by 4 respectively. So yeah, and now the problem asks us about like picking the correct picking the correct options. So maybe we can do this. Okay, again, let's try to do this option by option. So I think you guys have a feel of what we have to do in these kinds of problems. So let's see. So pick the correct option. So the first option says that the parameter k affects P2's payoff. Like, I think this is straightforward. The first thing is straightforward. Like, what do you guys think? Is the parameter k affecting P2's payoff? Like P2's payoff, P2 is the current player, so these are the payoffs for P2. The right side ones. I think this tuple, like here the P2's payoff is -1. Here it's 0, and it's 1. Okay, so Manas is saying that it seems that, oh yeah, yeah. So Manas, I think, got it. Like, yeah, uh, k is not affecting P2's payoff. So k can decide, like, with different values of k. Like, it might be that the equilibrium might get changed, and so what P2 gets an equilibrium might get changed. But in general, if you're speaking like what about P2's payoff, so P2's payoffs are not affected by k at all. P2's payoff at equilibrium might be affected, but in general, like, you can say that, right? Because equilibrium point can change with different values of k. But if, like, you're not talking about the equilibrium point, you're just talking in general about P2's payoff, then see that uh, P2's payoff is not affected by k at all. Like, it's a constant with respect to k. Whatever the value of k, here P2 gets a value of -1, here he gets a value of 1, here 0 and 0. So this option is incorrect. So good job, Manas. As P2's payoff is not a function of k. Right. Okay, maybe before coming to option B, let's discuss option C and option D. Okay. So option C talks about the types, like P1 has two types and P2 has one type. So although, like, it's not explicitly like okay, like this question is not very, like, I think this is just a very high level question, like it's not very formal, but I hope you guys, like, the main idea of putting this is like to give you guys an idea of types and everything. So like the option says that P1 has two types and P2 has one type. So note that there is no information given to us about the types here, like if one player has any two types or any player has one type. So usually, like, if we are strictly talking in a very formal sense, like the types should also be given to us in the problem itself. Like types can be arbitrary, and so like you can't decide unless it's specifically given if a player has one type or if a player has two types. But in this problem, like, types are not given to us, and the option asks us P1 has two types and P2 has one type. Is this true or not? But in this, like, on a very high level, you can kind of see that in the payoffs, like P1's payoff seem to be affected by K, but P2's payoff don't seem to be affected by K, right? So you can kind of think of this as like, I'm just talking on a very heuristic sense, like this is absolutely not true in a strictly formal sense, uh, but you can think of this as saying that like P2 just has one type, because like since P2's payoffs is like a constant with respect to K, so this means that P2 is not affected by the value of K at all. Like P2 is not affected by the value of K. Like P2's payoffs remain the same irrespective of the value of K. And so, like, it kind of seems to imply that P2 has one type. And like, since P1 values are affected by K, so P1 seems to have two types. Note that this is like, so this is just a very heuristic argument. Note that this is like, so just for sake of answering this question, like, we can say that this thing can be true. But in a very strictly formal sense, note that this is not correct. Because why? Because like it can be that P2 has two types, but in like realization of both the types, the payoff for P2s remain the same. Like it can be true, right? Like even if a player has two types, but the payoffs in both the types are the same. But strictly speaking, in a very formal sense, the players can have two types. So strictly speaking, P2 can have two types here, but the payoffs in both the types are the same. but in a very loose sense, like just for the sake of answering the question, you can say that P1 has two types and P2 has one type. Since P1's payoffs are parameterized by K, whereas P2's payoffs are not, we can loosely say that P1 has two types and P2 has one. So just adding a note here, in a strictly formal sense, this statement is incorrect as the type information should explicitly be mentioned in the question itself. It may well be true that P2 has two types, but payoff are the same in both types. Yes, so exactly, Manas. So P2 can have infinite types, each having same payoffs. Exactly. So that's why types are something which should explicitly be given in the problem itself. Like how many types does one player have, how many types does the other player have. You cannot make assumption on the types. But yeah, here like just loosely speaking, just for the sake of like answering the question, you can say this kind of thing happens. Uh, Consider P2 independent from P1, but dependency may bound to 2. So what does this mean, Manas? I don't get what you're trying to say here. Yeah, exactly. So yeah, so from what I seem to understand, you're just saying this thing only, right? Even though P2 is independent from P1, it can have two types, although both types have the same payoff. Is this what you're trying to say, or you're trying to say something else? Okay, maybe we can continue. Okay. Also, in infinite case, only two will have different payoff for. Okay, maybe. Yeah, exactly. Yeah, this is what you see. What you're trying to say is like, yeah, even though you can have like infinite types, like you can bound them to two just for the sake of analysis. Like many identical players can be thought of as one player. So yeah, that kind of makes sense. Definitely. And also, like, okay, one more thing which I want to point out, like in option D says that P2 has two types and P1 has one type. So again, because we were speaking loosely, we said that P1 has two types and P2 has one type. But I just wanted to ask this question. So note that payoffs for P1 are dependent on K, whereas payoffs for P2 are not dependent on K. But is it possible that P2 has two types and P1 has one type? Like this is something which I want to ask from you guys first. What do you guys think? Can this situation occur that even though payoffs, like, so what I tried to say is, like, can this happen that even though payoff for P1 are different in different instances of K, but still P1 has only one type? Can this kind of a thing occur? Or is it always true that if a player has only one type, then his payoff will remain same across all the instantiations of the game? Like specifically this part, like, yeah. Okay. Like, again, like, so on, like, based on payoffs, if you are just to answer, like, yeah, intuitive, like, on a very loose level, you can just say that, like Manas has written in the chat, that P1 has two types and P2 has one type. But note that in a strictly formal sense, it might well be true that P2 has two types and P1 has one type. So note that the payoff matrix is actually like a payoff for a player. Like, even though a player might not observe the value of K, but it might well happen that uh, that player still has like different payoffs at different instantiations of the game. Like it might be true that you might know not know about like one underlying factor. Like, think of this as in a real world scenario also. Like, you might not know the value of K, or you might not know, let's say, the whether it will, suppose, like, the K is a variable which tells me whether it will rain or not. Okay. And suppose I'm inside my house and I'm not able to, like, I don't know if it's raining outside or is it not raining outside, but it can still affect my, like, let's say, electricity or something. If it's raining outside, then there's a higher chance that electricity in my house will be cut. And yeah, if it's sunny outside, there's a lesser chance. Like, if there's not a thunderstorm outside, there's a lesser chance of a power cut in my house. Like, usually in thunderstorms, power cuts are common. I'm assuming, like, at least where I live, it's common, like, thunder during thunderstorms. So, so what this, like, even though you are inside your house and you cannot observe whether there's a thunderstorm outside or there's not a thunderstorm outside, still it can affect your payoffs. Like, it can affect, like, whether there's a power cut or there's not a power cut, which can possibly affect your payoffs. So just wanted to highlight that even though I only had, like, in this situation, one type, since I'm not able to observe whether there is a thunderstorm outside or not. But still, my payoffs are different in the two different instantiations, when there was a thunderstorm and when there was not a thunderstorm. So it can definitely be happen, and there have been examples given of this kind in the lectures also, where, like, even though a player has only one type, but his or her payoffs are different in the different instantiations of it. Do my arguments make sense, guys? Like, what I'm trying to get at is, like, you cannot deduce anything about types or number of types in a strictly formal sense, just from a payoff matrix. Like, you cannot presume there are lesser number of types or there are more number of types or even anything. So usually speaking, this is still correct. Let's see. So however, in a strictly formal sense, this statement can be true as layer can have different payoff in different instantiations of the game, even if a player has just one. Okay, is it is my audio better now, Manas, or is it still breaking? Like, was the should I repeat the argument for like why is it possible that this is true, or did you get that? Okay, it's okay now. So should I repeat the argument for this? like why is it okay even if P1 has one type? Or was that argument clear? Okay, maybe I'll just repeat. So maybe so what I'm trying to get at is the payoff, like it might be totally true that okay, so if P1 has one type, what it means is P1 does not observe what's the value of K. You can assume this means that P1 does not observe the value of K. But what I'm trying to say is even if P1 does not observe the value of K, it is totally possible that it still affects the payoff for the player, for a player. So even if a player does not uh, know like if a player does not see the value of a parameter, it is still possible that the parameter affects the player. So like it is totally possible that a player, even though a player has one type, he or she can have like different payoffs in different instantiations of the game. And what's a intuitive way to think of this, like why is this kind of a thing true? So what I'm trying to say is, suppose I'm sitting inside my house and I have no idea of whether there is a thunderstorm coming outside or not. So let's just say the K here denotes like thunderstorm. So if K is 0, then there is not a thunderstorm outside. If K is 1, then there's a thunderstorm coming outside. So what happens is I'm inside the house and I suppose I'm not going into the balcony, so I have no way of knowing whether there is a thunderstorm outside or is it like or not. But still it might be possible, like it's usually the case, at least where I live, that if there's a thunderstorm, then a power cut is more common. And let's say power cut affects my payoff, like if there's a power cut, then this means like I'm having somewhat of a lesser payoff. So even though I'm not observing whether there is a thunderstorm outside or not, so even though I have exactly one type, like which is just sitting inside the room, like I don't have two types, like one type based on there is a thunderstorm outside and one type based on there is not a thunderstorm outside, because I'm not even observing the thunderstorm at all. So it might be totally true that I'm inside the house and I don't know about like what's happening outside, but it might still affect the payoff. Like even though I have just one type, I don't know if there's a thunderstorm coming outside or not, but that thunderstorm can affect my payoffs. So my payoffs are affected even though I don't observe the value of the parameter K. So even if I have one type, yeah, so okay, so P1 having one type with impacting payoff by K, that's okay. But what about two types of P2? So again, like I previously said, precisely speaking, like P2 can have two types, right? Like 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 what we were discussing earlier also, like it might totally be true that payoff has two types, but in both of the two types payoffs are the same, right? So this was what we discussed in C option also, like strictly speaking P2 can have two types but payoffs are same in both the types. So here also P2 can have two types and the payoffs are same in both the types. But P1 has just one type. So like what I'm getting at is, by discussing the option C and D, is like you really cannot deduce anything about the types just from the payoff matrix. Types are something which should be explicitly given to you. Yeah. So yes, exactly, that's what I'm saying, Manas. So you cannot distinguish, like loosely speaking, like this I think like yeah, like precisely speaking, like option C and D both should be incorrect. But like I was just saying, like what this question seems to imply is they want us to look at something like A, but precisely speaking, this should be like not true. Like these, both of these can be incorrect in different instances. So precisely speaking, the types are something which should explicitly be given to us. They are not something which we can deduce just from the payoff matrix. Okay, so I hope this makes sense. Then maybe what should we do? Maybe we can discuss option B. Okay, so option B says that there exists a unique pure strategy Bayesian Nash equilibrium. Okay, so oh my god, if we have to check about okay, so it should be a unique pure strategy Bayesian equilibrium, right? Okay, so just for solving this problem, like I guess we'll have to like we'll just assume that P1 has two types and P2 just has one type. Like why I okay, like even though like both of these are incorrect, but why I said that loosely speaking, you should say this as true and say this as false, because given this problem, like there can be like strictly speaking, like this problem is incomplete. The data in this problem is incomplete. But suppose like it, there can be possible cases where these kinds of questions come up in the quiz or the exam. Okay, like yeah, these questions indeed come up, and then like the reasoning for types can be these kinds of things. Like if you see the payoffs and what's a constant and what's not a constant, and from that you can deduce the types, and like you need to know the types before like arriving at some Nash equilibriums or something. And why is this the case? Because like, I hope you understand like why do we actually need types. We really need types so that to know like how many like will a player be able to distinguish between two instantiations of the game, or will he not be able to distinguish between instantiations, and so on. So like for this, like so for like so just for the sake of this, like if you want to find out a Bayesian Nash equilibrium for this problem, like for the sake of this problem, we'll be assuming that P1 has two types and P2 has one type. Okay, and then like you can have like since P1 has just like since P2 has just one type, then P2 can either play just L or just can play R. So like if P2 has just one type and P1 has two types, then like P2 can just play L or P2 can just play R. And what this means is yeah. So if we are looking at a pure strategy Nash equilibrium, then like obviously like P2 cannot have a mixed strategy, so he will just be playing L, or he'll just be playing like R only and nothing else. So let's just see if we can find a pure Nash equilibrium. So suppose P2 just plays L. Maybe we should. Oh yeah. So suppose P2 just plays L here. So what this means is uh, uh, now hmm, okay. So if P2 decides to just play L, what happens is this player one now in this first game. So P1 has two types. So in the first instantiation of the game, player one's payoff when P2 plays L are something like if k equal to 0, then player one's payoff is like something like 3 here and 2 here, right? Okay, maybe I should just since P2 has one type and we are looking for pure strategy Bayesian equilibrium, P2 will play L or R, right? And now let's just see the case one. So case one is P2 plays L. So what happens if P2 plays L? So if P2 is playing L, like mm, so now what are the deterministic strategies, like what are the pure strategies for like player one in this case? So player one can play like in game one he can play like so there will be two instantiations of the game. So this there will be one payoff matrix in which k equal to 0, and in the payoff matrix k equals to 3. So uh, in the two instantiations, like you need to find the expected payoff over both of these instantiations, and like probabilities for the instantiations are 1/4 and 3/4, right? So like what will be the pure strategies for player one in this case? So player one can play like uh, T in one instantiation and B in the other, or like B in the first and T in the other, TT or BB. So these will be the four possible cases for player one in his or her deterministic strategies. So uh, possible. So we'll look at all of these and we'll see like what sticks, like uh, what's a strategy from which the player one will actually not want to deviate, and will then need to ensure if P2 will also not deviate from the strategy. Possible strategies for P1. So what will the possible strategies for P1 are? So it will be something like maybe I should again add bullets. So it will be something like TT. So it means that in the k equal to 0 case also, case and k equal to 3 case. So I have these strategies. So this will denote like he's playing T in the first case and T in the second case. So in this case, what will be the payoff for layer 1? So in this case, layer 1's payoff will be something like so with probability 1/4, the first game gets instantiated in which k equals to 0. So here, so if k equal to 0, then the payoff of layer 1 is 3 here on playing T. So on playing T, the payoff here is 3, and with probability 3/4, the other game gets instantiated, and in the other game, the payoff is in the other game, like the payoff is on k equal to 3, this is actually equal to 0. So this will be like with 3/4, the payoff will be 0. So here the payoff will be something like 3/4, right? And similarly, what we have for like instead of TT, we have something like, let's say, TV. Then like we know that P2 is already playing L. So in the case of TB, the possible will strategy. So with 1/4, the payoff will again be 3, and uh, like with probability, like in the second case, like his player one is playing B. So in the second case, player one gets a payoff of 2. So this will be 3/4 times 2, and this will be actually equal to 3/4 plus. So this will be 3/4 plus 6/4. So it will be something like a 9/4, I believe, right? Because it's 3/2, so it's 1.5 plus, yeah, it will be 2.5. And then the third pure strategy for layer 1 can be something like B comma T, and here what will be the payoff of layer 1? So in the k equal to 0 case, if he plays a B, then its payoff is like 1/4 times 2, and in the second instantiation of the game, so second instantiation is with probability 3/4. Here, if he's playing a T, our player 2 was already playing a L, then in this k equal to 3, so payoff is 0 in this case. In this case, his payoff is 0, and so in this strategy, his payoff will be something like a half. Okay. And now let's move on to the last possibility. So if the player plays B comma B, so I'm doing this like very explicitly, but you guys can do this orally also. Like I'm just doing this more explicitly so that everyone can follow what I'm trying to do here. So with probability 1/4. The first game it gets instantiated, and in this case he's playing B, and in second case, so if player 1 is playing B, then anyways like payoff is always 2. So it will be 1/4 times 2 plus 3/4 times 2. So this will be like equal to 2 only. So like out of these four strategies, like this seems to be the strategy which works out the best for. So if P2 is playing L, then P1 will be playing this strategy, this pure strategy. Like because in any other pure strategy, like player 1 will have an incentive to switch from any other strategy to this T comma B strategy, because this T comma B strategy gives player 1 the highest payoff if P2 is playing L. So if P2 plays L, then player 1 will have no incentive to switch. Okay, so what this implies is if P2 plays L, P1 has no incentive to switch from T comma B, right? So if P2 is playing L, then P1 will have no incentive to switch from T comma B. Now, but we also need to check if. So we have checked that P1 will have no incentive to switch. If but we also need to check if P2 will have an incentive to switch from L to R. So considering if P1 is indeed playing this T comma B, one still needs to check if P1 will be switching from L to R, like P2 will be switching from L to R. Like we know that if P2 plays L, P1 will stay at T comma B. But if P2 is playing T comma B, what's the guarantee that P1 will not move from L to R? And that's why we need to check this by ourselves. Like if P1 will stay at L or P1 will move to R. Okay, so let's just do this also. So what are the possible cases? So possible cases are if P1 plays L, okay, if P2 plays R, what's the payoff? The payoff if P2 is playing R will be something like so now we know that like P1 we have fixed as P1 will be playing T comma B, and now player 2 let's say plays R only. So what's the payoff? Then in the first instantiation with probability 1/4, the payoff for P2 will be something like player 1 will be in the first instantiation player 1 plays T, and in the second instantiation he plays B, and we are fixing P2 to play R. So in the first instantiation, okay, so player 1 plays T, and this is like payoff for P2 is 0 in this anyways, and similarly it's 0 in the other instantiation also. So in this case it's 0 only. So 1/4 plus 3/4 times 0. So this is the payoff for P2 if he plays R. But if P2 plays L, what's the payoff? So if P2 plays L, like if P2 switches from R to L, what's the payoff for P2? So it's something like if P1 is playing T comma B, so in the first instantiation with probability 1/4, the payoff for P2 will be this -1. So with probability 1/4, the payoff will be -1, and with probability 3/4, the payoff for P2 will be something like a 1. So this will be 3/4 times 1. So this will be actually equal to half. So this essentially means that like if P1 plays T comma B, then P2 indeed has an incentive to switch from R to L. So actually there will be no Nash equilibrium at so hence P1 playing T comma B. So essentially what this means is P2 will have an incentive to switch from L to R, and P2 has an incentive to switch from R to L, R to L, and hence uh, there is no pure Nash equilibrium, Bayesian Nash equilibrium, if P2 plays R. So if P2 plays R, there is no Bayesian Nash equilibrium. So the case 2 will be when P2 plays actually. So okay, I think. Oh, okay. I guess I screwed up a little. Sorry for this guy. So we were in the case when P2 was anyways playing L. So we were in this case, like when P2 was playing L, and that's how we wrote the payoffs, and we found out that T comma B is the best strategy. And then we checked if indeed P2 will be switching from L to R. But note that on playing L, P2 has a better payoff than on playing R. So P2 will actually don't have an incentive. So yeah, sorry, like we were sorry for this guy, like we were checking for P2 and playing L, and I like in the last line I kind of got confused and said something different. So P2 has actually no incentive to switch from L to R. So this is actually a Nash equilibrium. Hence P1 playing T comma B and P2 playing L is a Bayesian Nash equilibrium. Okay. So there is just one Bayesian Nash equilibrium if P2 plays L. Similarly, case 2 will be when P2 is playing R, and you can check for yourself in that case you won't be able to obtain like Nash equilibrium. So now we have a case 2. Yeah. So this is case 1. This is case 2. Maybe I'll just bold out these cases so that it's clear what's the high level. Yeah. So first we found out a Nash equilibrium when P2 is playing L. And now we are checking if there's another Nash equilibrium if P2 plays R. So if P2 plays R, like actually you can check that no Bayesian Nash equilibrium. And this will be an exercise for you guys. Like you can try this yourself. Like the arguments are like not too hard. Like all of these arguments were also not too hard. These just took a bit of time because I wanted to get everything written down explicitly. Okay. So like you will actually arrive at like there was just a unique Bayesian Nash equilibrium when in pure strategies when P2 was playing L, and there was no Nash equilibrium when P2 was playing R. So there was actually just a unique pure strategy Bayesian Nash equilibrium. There is a unique pure Bayesian Nash equilibrium. And we have already discussed option C and option D. And in option E, so option E is just talking about like which is a pure strategy Bayesian Nash equilibrium. And this T comma B and like P1 playing T comma B and P2 playing L, we already realized like in option B that this is the Bayesian Nash equilibrium. And this is what this option is talking about. If this is a pure strategy Bayesian Nash equilibrium. So it indeed is an equilibrium. So yeah, like true Okay, so I hope this makes a bit of sense. So if once again, so I think Manas has left the meeting. So Satvik, if you have any doubts at any point, like feel free to ask me in chat, and I'll try to answer it to the best of my capabilities. Okay. Then now we are in the now let's discuss the fifth question. So fifth question says that chess is a game of imperfect information. Is this true or false? This is a very high level question, I think. Uh, right? So Satvik, what do you think? Like, is this statement true or false? Like, is chess a game of imperfect information? So, exactly. So Satvik is saying that this statement is false because identities are known. Yes. So so this statement is actually false. So good job, Satvik. Or like, like why is this false? Like one way to think about it is like everyone knows the board configuration at every stage, as both the players know the exact board configuration after every, right? So like the players know like which is their piece, which is the opponent's piece, and which piece is at which position. So they can always distinguish between any two configurations, and that's why it's a game of perfect information. So good job, Satvik. So okay, now maybe we can have another question of like this type where we are discussing here. Maybe I'll just remove the last question, like otherwise it will be taking a lot of time. So we can just have what we can just discuss this last question for the day. One more question. So the question says that suppose P1 is the row player, P2 is the column player, payouts are dependent on the value of theta. So there's a parameter theta given to us, and like n is essentially the number, the two players which are given to us. So players are P1 and P2, and probability that this parameter theta equal to 0 is 1 by 3. So uh, so like this theta takes two values, so this theta takes the value 0, and like let me just and it takes the value, yeah. So this parameter theta takes the value of 0 with probability 1 by 3 and value of 1 with probability 2 by 3. And now after this theta takes the value, like P2 knows if theta is actually equal to 0 or theta equals to 1. But P1 does not observe the value of theta. So P2 observes the value of theta, but P1 does not observe the value of theta. So does this mean something about the types of P1 and P2? Atvik, would you like to answer? Like this is the kind of thing which we were discussing. Like, can I in this case say that P2 has like two types and P1 only has one type? So good job, Satvik. So exactly. So Satvik is saying yes. So note that like in previous question, like we had to find out the type from the pure matrix, which I said is not formally correct. But here, like you can precisely say that like since there is just one parameter theta, then like the instantiation of the parameter, if a player observes the instantiation, then a player knowing whether theta is 0 or theta is 1, like these are two different instantiations of the same player. Like, but one player which does not observe the value of theta will act regardless of whatever the value of theta is there. So you can think of P1 as only having one type, whereas P2 has two types. Okay. So maybe since P1 does not observe theta, but P2 observes theta, we can say that P1 has just one type, whereas P2 has right? Because P2 is observing theta, P1 is not observing theta, and now these are the two pair of matrices if theta is 0 and theta is 1. Okay, and now we have to pick the correct options for this game. Okay, maybe I should yeah, this seems I should just plot this image. Yeah, I'm just making this pair of matrices side by side instead of them being. So we have these two pair of matrices like theta equal to 0 and theta equals to 1. And now, and we know that theta equal to 0 occurs with probability 1 by 3 and theta equal to 1 occurs with probability 2 by 3. And now we have to find out the correct options, right? So maybe like since this is irrelevant, maybe we can just toss this out. Like so, like the high level idea for this is that, like so the main observation is like P1 will have P1 will just be choosing from T or B, whereas P2 will be choosing like L and R based on the two different instantiations of the game. So P1 will just choose like a strategy from T or B, whereas P2 will be choosing a strategy based on the state of the game, like a different strategy for theta equal to 0 state and different strategy for theta equal to 1. Okay, this is what I want you to suggest. So now the expected payoff of P1 from T. So if P1 plays, let's say, just the strategy T, like suppose P1 is directly playing the strategy T, then what's the payoff of P1? So if let's say P1 is playing the strategy T, then let's see what happens. So if P1 plays strategy T, P1 plays the strategy T, then what happens is like in this theta equal to 0 case, what's the best response by player 2? So player 2 is the column player. So column player will have will play either L or R, and the column player will want to maximize his payoff if the row player is playing T. So column player knows that between -1 and 1 he'll choose this one. So column player will play R in the theta equal to 0 game. P2 plays R if theta equals to 0. So maybe I'll just and if theta equal to 1, if player 1 is playing strategy T, what's the best response by player 2? The best response is playing L here because his payoff is 1 here and -1 here. So plays L if theta equals to 1. Because these are like, why is these true? Because these are best responses for P2, these two instantiations, right? And note that like P2 can choose between, like since P2 observes the value of theta, P2 can have this kind of a condition like if theta equal to 0 and if theta equal to 1. Okay, and so what will be the expected payoff for P1? So expected payoff for P1 from T, what will this be equal to? So it will be equal to payoff when in theta equal to 0 case, the payoff in this column, like in -1, 1 column, because player is playing like player 2 is playing this part, and similarly in this part player 2 is playing like here T comma R will be the what will be played, and here T comma L will be played. So in T comma R, what's the payoff for player 1? It's like -1, and this theta equals 0 occurs with probability 1 by 3. It's 1 by 3 times minus 1. And this game occurs with 2 by 3 probability, and payoff for player 1 is 1 here. So it will be 2 by 3 times 1. So this will be actually equal to 1 by 3. So Satvik has already written the chat. The answer is 1 by 3. So good job, Satvik. So this is the answer for from T. And similarly, if so, let's just copy and paste this, and like let's just see for the strategy B what will be happening. So if strategy B is chosen by the player, then what will be the best response in theta equal to 0 case? By the column player, it will be L in this case. So place L if theta equal to 0, and here the column player will play, again the column player will play, because best response for column player in both these cases is like in one, like in the bottom row is like L only. So in both the cases, like column player plays L. So what will be the payoff for so this B comma L will be actually what we'll have as the, like in both of these cases B comma L will be the final state of the game. So expected payoff will be like 1 by 3. This happens with probability 1 by 3. So it's 1 by 3 times minus 1, and it's 2 by 3 times again a minus 1. So it's like 2 by 3 minus 2 by 3 minus 1 by 3, which is minus 1. So if player 1 plays the strategy B, so this is something B, then like by the best responses of player 2, like we get a payoff of minus 1. Okay, maybe, yeah. So this was the option what I meant to write. Maybe I just entered it. So yeah. So yeah. So I hope this makes sense. So on playing T, expected payoff is 1 by 3. On playing B, expected payoff is minus 1. So option A is correct. Option A is correct. And similarly, like for option B, so option B says expected payoff is minus 1 by 3 and 1 by 3. So this is like this one. This is 1 by 3. And so this is incorrect. Like, and why is this the case? Because we have already discussed in option A. It's correct. If option A is correct, so option B is already incorrect. Right? So now the option C says, so option C says that if P2 plays R for theta equals 0 and L for theta equal 1, then what's the best response for P1? So let's just choose it by ourselves. So if P2 plays R for this, then the payoff for P1 is, so let's just check the payoff for P1 and maybe like we'll do this. Yeah. So the case 1 will be like there are two cases like in terms of pure strategies, like P1 plays T or P1 plays D, right? Maybe I should just so now yeah, maybe that like that U and R was just like T. So if P1 is playing something like T here, so what will be the payoff for, like if P2 is playing like R comma L, so P2 is playing R here and L here, what will be the best response for P1? Like, or maybe just what will be the expected payoff if P1 is playing T? So if P1 is playing T, the expected payoff will be like this theta equal to 0 occurs with probability 1 by 3. So here it will be 1 by 3 times this thing, like L comma R is what's chosen. like L. Okay, no. R is chosen by P2 in this case, and L is chosen in this case. So R comma L is chosen, and in this case, if R is chosen and P1 is playing T, what's the payoff for P1? It's like -1. So it's -1 times 1 by 3 plus like 2 by 3 times 1. Like this was the condition in which we discuss here also, like P2 plays R and plays L if theta equal to 1. Right, and here we got expected payoff is 1 by 3. So this is what the expected payoff looks like. Right. So this is the same, and like if P1 plays instead this B, then what's the expected payoff? So if P1 is playing this B, in this case, this is chosen because P2 is playing R comma L. So this is the outcome for the game, and like the payoff for P1 is here 1. So it's 1 by 3 times 1 and plus 2 by 3 times. So it's 2 by 3 times, and here the payoff is like this one. Here it's -1, right? So 2 by 3 times -1. This will actually come out to be equal to -2 by 3 plus 1 by 3, which is -1 by 3. Okay. So like best, so and payoff on playing T is better than payoff on playing B, expected payoff. So T is the best response. Yeah. So T is the best response of T. And now we can go to option D. So what we observe is that like so what we observed is that like for the strategy of R comma L, like R if theta equals 0 and L if theta equal to 1, like T is the best response. Like T is the best response for this strategy, and for playing T, like R comma L is the best response. Like in option A, we saw that player 2's best response to the strategy T was R comma L, and in option C, we saw that player 1's best response for R comma L is indeed yeah. So exactly, like this is what Satvik has also written in the chat. So yeah, it is a Bayesian equilibrium because everything is a best response to each other. So since options A and C are correct, uh, the given is a Bayesian equilibrium. So option A was correct, option C was correct, and option D was correct. Right? So options A, C, D. So good job, Satvik. Okay, I guess yeah. We although we just discussed, I guess this is it for the day. Like we just discussed 6 questions today, but I think these questions also needed a bit of calculations, and yeah, that's why I think it took a bit of time. Like we are like, okay, I think we are out of time, and like, we have even overshot by 10 minutes. So yeah, I guess this is it from my side, Satvik. So if you have any doubts, maybe I can try to clear those in like maybe next 5 minutes. Uh, or if you don't have doubts, like we can also like close the session. Okay, so are you typing something, Satvik? Okay, I don't think Satvik is typing anything. Okay, so I assume that uh, you don't have any doubts, Satvik. So in that case, I guess we can close the session. So yeah, once again, thanks for joining the session. And to the YouTube audience, hopefully I'll see you guys next week in person, same timings, 6 to 8 p.m. So yeah, till then, see you guys and good luck for the quiz. So I'll be closing the session now. Goodbye, Satvik. Thanks.